you. Good afternoon. Okay, I'm going to talk about the role of biological connectivity at genetic and community levels. This has been a work with researchers, both from devoted partners, but also from external researchers. Okay, the neutral theory of biodiversity has been inspired by the neutrality concept of molecular evolution, and states that in an ecological community of similar species, diversity arises at random, which is the so-called ecological drift. Both theories predict that genetic similarity and community similarity decreases with geographical distance, and this depends of dispersal limited. So the idea in this study was to compare these two levels, different groups, phytoplankton, zooplankton, and benthic and macrovertebrates, and with the aim to propose vulnerability indicators. And apart from phytoplankton and zooplankton, we also split the group of benthic macrovertebrates into functional groups. So those that take into account the pelagic phase and those that do not take into account this pelagic phase. For the community analysis, we compiled a large set of data from phytoplankton, zooplankton, and macrovertebrates across the different seas of Europe. For instance, for phytoplankton, we recorded more than 500 species of diatoms, and flagellates, and coccolithophores in 36 stations. So the stations, that means we take all the information in a time series. Also, in the macrovertebrates, we centered to the soft bottom, and for instance, we compiled more than 2,000 species that has been spread in nearly 600 sampling units. Okay, so from all this information associated to these sampling units, we take into account environmental data like sea surface temperature, salinity, oxygen, and also other ones that are specific for the group. Also, we took into account the distance. First, the oceanographic distance, and also the community similarity, which is the proportion of shared species between the two sites. From all this information, we correlate using mantle, and what we obtain is that for all groups, the correlation between species similarity and geographic distance was higher than between species similarity and environment. And this allowed us to infer the dispersal scale using the halving distance method, that is the distance at which similarity is half of its initial quantity. Okay, so from this dispersal scale, we obtain the results in that sense that, for instance, for microzobenthic non-dispersal larvae, the dispersal scale was lower than the macrovertebrates with dispersal larvae, and this was lower than phytoplankton, and in turn lower than zooplankton. But this is just a snapshot of a network. We can see some patterns of biodiversity comparing phytoplankton, zooplankton, and the right one, the macrovertebrates. Concerning the genetic data, we perform a meta-analysis that take into account nearly 150 papers addressing 22 species of zooplankton, 13 species of phytoplankton, and 77 species of macroinvertebrates. From the genetic information, the coordinates, we calculate that isolation by distance is low, which is called IBD, and if this is significant, we can infer the dispersal scale is formal. So we obtain this kind of table of more than 100 species where we have both the IBD slope and also the dispersal scale. So the results, the statistical results of this obtained again, similar to the community, that the macrozooventus of non-dispersal larvae has the dispersal scale lower than the microvertebrates with dispersal larvae, and this is lower phytoplankton and zooplankton. So the conclusion is that dispersal distances rank the biological groups in the same order at both genetic and community levels as predicted by organism dispersal ability and also the seascape connectivity. This has recently published and supports the prediction of neutral theories, marine biodiversity patterns, and can maybe have some practical consequences for biodiversity conservation, the Marine Strategy Framework Directive. Thank you very much.